Hello, I'm Greg van Buskirk, and I'll be talking about sparse convex hull coverage. This is joint work with Georgiy Klimenko and Benjamin Raichel. So for a brief motivation, a common goal in computational geometry is sparsely approximating geometric objects. And one well-studied object is the convex hull. So it's natural that people would be interested in sparsely approximating convex hulls for some measure of error. And applications of this include polygon simplification, feature selection in machine learning, and just reducing space complexity. So it is natural, and in fact others have studied this before, and most previous work considers minimizing a max objective, which we'll see in a second. And instead, this paper we're going to consider minimizing a sum objective, which arguably is more robust to outliers and useful for certain applications in machine learning and data science. So here's the basic problem. We've got a point set P of endpoints, and we're trying to select a subset Q of at most k points, which minimizes the objective. So like I said in previous work, the objective is a max, so you look at the distance from each point x to the convex hull of Q, and then you take the max of all those distances. And then in this paper, we're instead going to just take the sum of all those distances. So here's a simple example just to illustrate the difference. We've got some points, and here's their convex hull. Now this red triangle is minimizing the sum objective. So you see it's kind of ignoring that point in the upper right, and it's instead this triangle is focusing on this sort of cluster of points on the left side. Now this triangle is minimizing the max objective, and you see it's kind of ignoring this sort of cluster on the left, and it picked that point in the upper right. You could say, in certain situations, you could argue that that point in the upper right is an outlier and it should be ignored. In certain applications, you could say the sum objective is more natural. Now, we're actually going to generalize the basic problem in two ways. First, Q no longer has to be a subset of P. It's now going to be a subset of R, where R is arbitrary. And then second, each point in X can be weighted by its own weighting function. So here's the general problem statement. Now we have two sets, P and R. And we're trying to select the subset Q of R instead of P of at most k points, which minimizes this. And this is basically the same as before, except you see the distance from x to the convex hull of Q is now going to be fed through this function gx. So here's an overview of the results. In dimension 2, we can solve the problem exactly, and we split the problem into two cases, whether p equals r or not, and you can see the running times there. And then in higher dimensions, we again split the problem into two cases, and we have hardness results. And then we have an approximation algorithm, which I'll say more about later. So in the plane, if P equals R, basically what we do is we reduce our problem to finding the minimum cost k-length cycle of a certain directed graph. So say we've got these points in the plane, and then just notice you can also view these points as vertices in a graph. A complete graph. So say here are the edges, and now these edges are going to be directed, but I didn't draw arrows just because that would get really messy. But now notice in this graph, if we have a cycle like this cycle corresponds to the convex hull of those 3 points in the plane. So that's kind of the basic connection. We're connecting cycles to convex hulls. And what we're going to do is we're going to weight the edges of the graph in such a way that the cost of a cycle is the same as the cost of our objective for convex hulls. So that's the basic idea. Now, let me just briefly try and show you why P equals R is important here, because this graph approach doesn't work if P does not equal R. So basically, so say we extend those two lines with the dotted lines, and we have this yellow region, and you see there's a point in that yellow region. So if you look at the cycle, if we're looking at this as a convex hole, you can see if we do an exchange, if we replace that one vertex with this one, you can see that this new convex hole decreases our objective because that previous point is now inside this new convex hole. And when p equals r, we can always do this exchange. But when p doesn't equal r, then we can't necessarily do this exchange. And things break down because of this. And that's sort of why the graph approach doesn't work if p does not equal r. Now, let me just briefly try and show you how we weight the edges of the graph. So, well, first of all, the vertices of the graph will be the same as the points in the plane. And the way we weight them, we've got these half spaces, h, p, q. So that'll be the half space that lies to the left of the segment from p to q, that blue region. And then the way we weight the edge, pq, is we just sum up those red lines. So all those points in the blue region, we look at their distance to the segment PQ, which are those red lines, and we just sum them up, and that's the weight we give to the edge PQ. So that's the basic construction of the graph, and then we just, like I said, we compute the minimum cost k-length cycle, and that will correspond to the optimal convex hole for our problem. And here's the theorem statement. And so this running time, n cubed log k, that's coming from the time that it takes to compute the minimum cost k-length cycle in a graph. So now when p does not equal r, we have to do something different. Basically, it's going to be a dynamic program. So say we've got this capital V is a point set in convex position, and we have these two definitions, slab and cone. So slab is going to be the region outside the hole that projects onto the segment VI minus 1 to VI. Cone is going to be the region of the plane outside the hole that projects onto VI. So you see in the picture, the slab is the blue region and cone is the yellow region in the plane. So now with these definitions we can see, so we've got this convex hole, the black edges, and we see that the slabs and cones sort of partition the plane. And we can then decompose our objective. So our objective, we got the FVP is equal to, that first equality is just the definition from the problem statement. And then the second inequality is the decomposition. You're just summing up the yellow and blue regions, the cost of the that the points incur in the yellow and blue regions. So now, an important thing about the plane is that there's a sort of linear ordering of these regions, and that allows us to do a dynamic program. So just briefly showing you kind of the idea. So this is a point set that we've got. First, we need to guess the lowest point in the optimal solution. So say this red square is our guess. Then we will guess the next vertex, V2, and we see that this red line here, that the cost that is incurred there is going to be fixed. It will not change depending on the next vertices that we pick. So that red line is going to stay the same for the rest of the algorithm. So now we guess again, we guess V3, and now again, these new red lines in the yellow and blue regions, those again are fixed. So we kind of have this linear ordering, and it's basically pretty straightforward to write down the dynamic program for this. So this is the case when p does not equal r in the plane, and that's the running time. So for hardness, the decision version of our problem, we ask if there's a subset Q of R of at most k points such that the objective is less than a given epsilon. And we're going to reduce from this problem called polytope vertex cover. So a convex polytope is a graph where the vertices are points in 3D which are in convex position, and the edges of the graph are the edges of the convex hole. of those points. Now the problem definition, we're given a convex polytope and an integer k, and we ask if there's a subset U of k vertices such that each edge is incident to a vertex in U. And Doss and Goodrich proved that this problem is NP-hard. So for our reduction, so technically it's in 3 dimensions, but drawing 3-dimensional figures is difficult, so I've instead drawn this 2-dimensional figure, so it's easier to see what's going on. And so if we say this triangle is our polytope instance, what we're going to do is for each edge of the polytope, we're going to construct a new point. So here we see these 3 red points. So what you do is you go to the midpoint of each edge, and then you move outward sort of orthogonally away from the edge a certain distance, and then that's your new point. So remember, in our problem we're selecting a subset Q of R, so R is going to be the black vertices, which are the vertices of the polytope, and we're trying to cover all of the points, so including the red points. So basically the reduction is pretty simple. We have these distances right now to the full polytope, and then if each edge is incident to at least one vertex, like here, so now the left vertex is not chosen, but still each edge is incident to a vertex, we see that the distance of each of the red points to the hole right now, which is just a line segment, that distance didn't increase that much. However, if there's an edge where it's not incident to any vertex in the subset that we choose, then that distance, at least for P1, has increased by more. And we basically just set the distance, right, the distance that we move the red points away from the edge, we set that distance in an appropriate way so that the reduction will go through. And this is the case when P does not equal R, and for the case when P equals R, we have to lift into one more dimension. So that's why the hardness for that case is for D greater than or equal to 4. So for the approximation algorithm, it's similar to greedy set cover, but instead of sets we're going to pick simplices, and instead of uncovered points we're going to consider how much our objective improves. So again, this should be in 3D, but just for simplicity we're going to do it in 2D. So say we have these points, and this red triangle is the first simplex that we greedily pick that improves our objective the most, and now it becomes the convex hole. And then we do it again, we pick another simplex greedily, and look at the convex hole of all of the points chosen so far, which is this. And then do it again, pick another simplex, look at its convex hole. So now we have this. So just like in the greedy set cover, the approximate solution can pick more points than the optimal solution. So in this example, so here, this picture has 6 points. So this is the optimal 6-point solution here. And we can see that for this optimal solution, you can triangulate it into simplices. And these simplices partition the points based on the nearest simplex. And so also notice that these simplices were available to us in the algorithm. We could have picked any of these simplices. So from those two observations, you can see that it's basically set cover, and that's how the analysis goes through. Now, so in 3 dimensions, the optimal k-point solution has O of k simplices. So thus in 3D we get a 1 plus epsilon approximation using O of k log n over epsilon points, which is similar to set cover. And then in higher dimensions, the simplex complexity grows to O of k to the floor of d over 2. So really this approximation is really only practical for low constant dimensions. So that concludes the talk, and thank you for listening.